Okay, looking a bit at logs. Remember we have an input from grade 11, from grade 8 to grade 11. We've got an x as an input. And we put in that x into the function. The function works like a machine and it does something to the x. And it outputs it as a y. But from grade 12 onwards, we're going to look at kind of the reverse engineering of that. What if we put the y into the function and can we tell what the function did to it and in terms of x? And so we put y as an output into it. Okay, so the inverse function is the one we're looking at in matric. The inverse. It's when you, for instance, turn your shirt inside out. What is that inside out? It's the backwards method. So the backwards method, if I say, for instance, the backwards method of 4 squared is 16. How do I backwards method that? 16, the root of 16, or the square root of 16, it was a 4 here and a 4 here, and I times it together to get area, which is 16 centimeters squared, if it was centimeters. And what's the backwards method to see what this length originally was? Well, I'm going to square root it. I'm going to get 4 centimeters in one dimension. So the backwards method would be the square root of 16. So square root is backwards to a square, and we ask the question, where did the square come from? Where did the square come from? Okay. A function puts out an output, and now we're going to take the output and reverse the process. Reverse it. And see what the function did and get an input back out. Reverse. So an inverse function is looking first at the output. We're looking first at the output and asking, where did this come from? Very important. This is the question we're going to ask. Where did this come from? This y output. Okay. If I've got an exponential function, so say for instance I've got an exponential function of 2 to the 5 is 32, and that's a function. What happened inside the function? Well, I put in 2, my input was 2, and I had a machine that doubled it, okay, that doubled it an amount of times. And my output, okay, so 2 doubled it amount of times, and my output is how big is it? And that's the question you're going to ask. How big is it after this function has done something to it? Now this doubled it, obviously we can see that it doubled it 5 times if it is 32. So how big is it? 32. What did I put in? What did the function do? It doubled it an amount of times, and we can clearly see it doubled it 5 times. So 2 times 2 times 2 times 2. So this function grows the number. It grows the number. Okay? It grows the number. In other words, there's a growth rate. Okay? There's a growth rate. So my exponential, we're going to ask, how many times did it grow and how big did it become? So if I've got 2 to the 0, how many times did this thing grow? 0 times, and I'm just going to get 1 out. Not even going to get a 2 out. 2 to the minus 1, how many times did it grow? Minus 1 time. In other words, it grew negatively the other way around. So it's going to become half of its size. How big did it become? Half. If I've got 2 to the 2 times 2 to the 3, why not? I've got how many times did it grow? It grew 5 times. And how big did it become? It became 32. So this number here, 2 to the 5, that 5 is how many times? And that is a growth rate. Okay, that is a growth rate. And how many times is the machine that we're putting it into? It's the machine of how many times. This is what the machine is called, how many times. Okay, the machine of how many times. It's exponents in reverse, or the backwards motion of exponents. So let's see what we've got here. We've got a new tool to see how many times that number grew. Okay, and how big it was. So if I've got log base 2 to the 1 equals, what am I saying? I'm saying I've got 2, and how many times did it grow to get this to a 1? And that's always going to be 0. If I've got log base 2, how many times did it grow to get to a half? It grew negatively. Okay. Today that thing is a half. Yesterday it was a whole. It grew negatively. So I put in a number into my machine and it becomes 32. How big is it to become 32? How many times did that thing grow? The growth rate was 5. Let's just do a few examples. So what does this really mean? It means that 5, and it grew y times. And how big did it become? It became 25. Now, log base 3, what's very good is that it's called base. So we can see that this thing is a base because we call this a base and we call this a power or an indice. So when I say log base 3, you can definitely see where that base is. So log base 3 of 1, so it became 1, so it didn't even grow, so it was 0. Log base 4 of 1/64th. How many times did this thing grow? Well, it obviously grew negatively because it's much smaller than it was, but by how much? So we can say 4 to the x. I'm going to use x as my variable for now. Because I choose to, I can use y as well. Let's use y actually so that we don't complicate things. 4 to the y is equal to 64 is 4 to the 4 times 4 is 16. 16 times 4 is 64. So 4 to the 3 minus 3. Drop the bases and I've got y is minus 3. So this thing grew negatively by minus 3. It kind of went back in time if you think of it in that way. Log base 8 of anything of log base 4 to the of 4, log base 32 of 32 is always going to be 1 because the growth rate was 1 because it stayed the same. Write in log form. Here's my base, here's how big it became, and that's how much it grew. So log base 8 of 64 is how big it grew, is equal to, because that's my real question, how big it became and how many times did it grow. It grew 2 times. Log base 3 of 1/81, which is 9 times 9, but it's also 3 times 3 is 9 times 3 is 27 times 3 is 81. So log base 3 of 1/81st is the same as saying -4. Why? Because 3 to the -4 is going to give me 1/81. Remember, your square root means this. Okay, it means x to the half. let's put that a little bit differently. It means x to the half is equal to y. So I've got my base, I've got how much it grew by, and how big it became. Yes, how big it became. So I'm going to go log base x of y equals, what was the growth rate? What was the growth rate? It was a half. Okay, good stuff. Okay, so for each function, write the equation of the inverse of the form, and that's f for inverse. Don't get muddled with calculus later on. This is f derivative, which is the gradient, tangent line, calculus, all that kind of stuff. So we want an f of minus 1, which is the inverse. Now the inverse is swapping the x's and the y's. It's putting the y as an output as an input instead. So what are we going to do? We're going to first log this guy. So this guy is actually y is equal to 3 to the x. Now, what's its base? What was its growth rate? How big did it become? And those are the questions you're going to ask. So here we go. We've got log base 3 of y equals, what was the growth rate? It was x. Now, very importantly, we need the inverse of this guy. This guy is still in this form. To get f of minus 1, which is the inverse, x, I need to swap these x's and y's. So I need to have an x here and a y here instead. So what am I going to do? This always represents y. Okay, the f of x, or inverse of x, always represents the y point. So I've got log base 3 of x is y, or is f inverse. Cool. So what did we do here? Number 1, we turned it into a log. So 1, we turned it into a logit, we logged it. Number 2, we swapped the x and the y. And this is the process you're going to go through, x and y. Okay, this is a very important process. Let's see our next one. We've got f of x is a third to the x. So this function is decreasing as x goes along. So what is this function? Y is equal to, I put in a third, and it grew by x to give me y. So number 1, I'm going to log it. Log base a third of y is equal to the growth rate. Then I'm going to find my f inverse, f of minus 1. X is equal to, and I'm going to swap my x and my y. Now you can write it out first as log base a third x equals y, but I know that this y is going to be my f of minus 1x, so I can immediately write it in that form. Okay, so I don't need to write that first. If you want to, you can, but time is money in your math exam. So more haste, less speed, but still be very astute with your time in your exam. So here we're going to go log base a third of x, and that equals y, or my inverse. Next one, I've got y is equal to, and I've got 5 over 2, and how much did it grow by? It grew by x. Let's log that thing. Remember, I'm just turning this into a y so you can see the y nicely. This f of x part. So log of base 5 over 2 of y, how much did it grow? It grew x many times. Now I'm going to do the inverse, and let's say if inverse x equals, swap my x's and my y's, that's how easy it is, swap my x's and my y's, and I get, do I have enough space here? Let's get a little bit more space. A little bit more space. So, yes please. So I'm going to have if inverse of x is equal to log base 5 over 2 and x, and that's my equation. Those are my equations for the inverse. Now, how do I draw this thing? How do I draw this thing? If they ask me to draw it, how am I going to draw it? Koek sister weet how to draw a log. You can put it into GeoGebra, GeoGebra is a very nice graphing graphing calculator, and it can graph for you, but we don't know how to graph logs straight away. But what do we know how to graph? Well, we can graph exponentials, we can graph hyperbolas, we can graph parabolas. So start with what you can graph. So let's look at this function. Y is equal to number 1 if I'm going to graph all of these. So I'm going to go, and I know that this is going to be an increasing function because my base is a 1 or bigger than 1. Your base can't be 1, otherwise it'll just be a dot, it won't go anywhere. So I've got y is equal to 3 to the x. Now, please do this. I'm going to make this a little bit shorter. Please do this. When you graph your function, some people do it in the horizontal method. I do vertical because then I can see my coordinate pairs very easily. So if I've got if x is something, what is y for this function? And I'm going to say -1, I'm going to say 0, and I'm going to say 1. You can add some more stuff on later on if you want to, but that's my basics. So if if I've got 3 to the -1, what is my y? It's going to be a third. Okay. If I've got 3 to the 0, that's always going to be 1. If there's no shift over here, there's +0. Okay. If there's a +0 in inverted commas, there's no shift up or down. And when there's no shift up or down, that thing is always going to hit y is equal to, when there's no shift up or down, or if there's no shift over here, because that thing can shift a little bit here, there's no shift, then we're looking at y is going to hit that one on the y-intercept. Why? Because anything to the 0, y-intercept, x is 0, is always going to be 1. No matter what this number is, it's always going to be 1. Okay, cool. So if x is 1, then y, so 3 to the 1 equals, y is going to be just 3. And those are my coordinate points, and this is why I like to do it vertically. It is 1:30 in the morning, 12:30 at night, so keeping my diction perfect vertically, because then I immediately have a coordinate pair, so I can do the coordinate pairs quite easily. So quickly, rough draft, it's going to look a little bit like this. Now please label this f of x, or label it what they tell you to label it. If you mislabel it, y is equal to 3 to the x. Now very importantly, can't touch this. Okay, that was a bit out of key, but oh well. Can't touch this. Your asymptote tells you where this thing is going to tend towards, so it's going to tell you where that shape is. And that's quite vital. So this asymptote is on the x line. It can go infinitely close to x is 0, but it cannot, but y is 0, sorry, but it cannot touch. So y is equal to 0 here, 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 here. That's why we call this line y is equal to 0. So the asymptote is at y is equal to 0. Please plot this as well and say your asymptote is y is equal to 0. Why? Because now that we've graphed this f of x, now what did we do in order to find f of the inverse? Yes, we swapped the x's and the y's. Now what do we do in order to graph this graph? Yes, we swap the x's and the y's exactly like we did before. So I'm going to have x and y, except I'm going to swap the x's and the y's. So this guy's going to be a third, and this guy's going to be minus 1. Can you see why doing it vertically, you can choose any numbers you want, but minus 1, 0, 1 is kind of uniform. We do it vertically so that we can quickly find those coordinate pairs, so that we don't go astray. There's a coordinate pair, there's a coordinate pair, there's a coordinate pair. Now we swap the x's and the y's. One more y and x to swap, very importantly, is going to be here, our asymptote. Now my new asymptote, you need to put in your asymptotes, especially for hyperbolas and for exponential graphs. You got hyperbolas, you got 2 asymptotes. Exponential graphs, you got 1. In a parabola, you need a turning point or a line of symmetry, that minus b over 2a. Okay, but for these, you need to swap the x's and the y's. So now x cannot be 0. And where is x 0? X cannot be 0 here. So you know that this thing is going to tend towards the asymptote but never touch it. And then tending towards shows us the shape. Okay, so this is kind of a rough sketch, but I've got 3 coordinate pairs, and I'm kind of going to go like that. Now, please name it. Please name it. Whether you name it a log or whether you name it f inverse x, please name it and put your coordinate pairs down. And can you see that it goes around this line of y is equal to x, or x is y is equal to x, or x is equal to y? So it reflects like a mirror along there, but that's not the way they're all going to reflect, because some of them will reflect differently. So I'm going to draw out for you some of these other ones, and you can just check to see if you got the same thing. Okay, so remember that this thing shape is going to tend towards the asymptote, which means it gets infinitely close but it doesn't touch. And please remember to name it f of inverse x, or if you want to, y is equal to log base a third x of x. Please put your asymptotes in, even write them in. This is x is equal to 0. That's what that line is called. And there you have it. Now this reflects a little bit along this line. Where's this line? This also reflects strangely along this line, y is equal to x. Very strangely along it, but in a different sort of way. You've got to turn your paper a little bit more to really see how it has reflected. Okay, so we've got y is equal to 5 to the x, and that was the exponential graph that we do know how to draw. And in order to draw the log graph, we're going to swap the x's and the y's in our vertical coordinate pair that we made. I like to use -1, 0, 1 because it works pretty well. Swap them and you'll find the log. Remember to draw in your asymptotes and name your asymptotes. X is 0, y is 0. And then can you see it goes along the y is equal to x line. Okay, so it mirrors quite nicely over there. So that would be the line of reflection. Okay, good job. Okay, so now we ask exactly the same question in a different way. For each function, write the equation of the inverse in the form of f of -1 x. Don't call it f of -1, it's actually f inverse of x. And we're going to do, now we did log and then we swapped the x and y. Now it's already log, we need the inverse. So we're going to take the exponent equation. We're going to take the exponent and then we're going to swap the x's and y's. So take the exponent form and then swap x's and y's. So let's see, what does this actually mean? It means y is equal to log base 4. How big did it become? It became x. So what is this really if I turn it into exponential form? That is base 4. How many times did it grow? Y is the growth rate. How big did that thing become? It became x. Now I'm going to swap my x's and my y's to find the inverse. So now I've got y as the subject, so I can immediately put it through here to f of -1 of x. I should put of x there, is equal to 4, and we swapped the x's and the y's, so 4 to the power of x. And let's do another one. So we've got y is equal to log base 1/4, and how big did it become? It became x. Now we're going to turn it into an exponential equation. I've got base 1/4, and how many times did it grow? What was the rate of growth? Was y is equal to how big did it become? It became x big. So now what I'm going to do is I'm going to swap. We need to swap our x's and y's. That's the second step, because inverses are swapping of x's and y's. So if I swap my x's and y's, y is now the subject. That's what you put in. -1, which is the inverse of x, is equal to 1/4 to the power of x. So y is equal to, or my y to the -1, inverse is 1/4 x. Let's carry on. So what does this really mean? It really means I'm just rewriting in this step. I'm not doing anything different. I'm just rewriting it so I can very plainly see the y. Okay, so y is equal to log base 6. How big did it grow? To x. Let's change that equation. Number 1, we change it into an exponential equation. So base 6, what was the rate of growth? And how big did it become? It became x big. Then we're going to swap the x's and y's. So I've got an x here and I've got a y here. That y can go directly into that f inverse of x is equal to, I've got 6, and now I've got to the power of x. Cool. Now when they ask you to draw this, we know how to draw the exponential graph each time. We know how to draw the exponential graph. So you're going to always begin with the exponential graph, because that's the one that you know. So if I draw this thing, I'm going to say f inverse of x. So that's y is equal to 4 to the x. I'm going to draw my vertical table of values, x, y, and I'm going to, if you ever have a problem with any graphs, parabolas, hyperbolas, anything, go back to drawing this vertical coordinate pair graph. I tell you why, because it proves to your mind and it proves to your brain and you need to prove to yourself things. You can't just say, well, this is the way it is because it is. Go back to this and say, okay, if this is x, this is y. If this is x, and this is y. And draw it out, and you'll see it, and your mind will believe as you proving it to yourself. That's why we always do proofs with things like identities in trigonometry and in geometry. We do all the proofs not just so that you can write an exam what the proof is and they can give you marks, but so that you understand, that you prove to your brain and your mind that this thing really is true. It's a very interesting paradigm. So go back to this. Say x is -1, and if x is 0, and if x is 1, and then plot the shapes of all of those graphs that you might struggle with. Okay, so this thing is y is equal to 4 to the -1. This thing is y is equal to 4 to the 0. This is y is equal to 4 to the 1, which is a quarter here, which is always 1 here unless there's a shift, and which is equal to 4 over here. So if I plot the points nicely of this inverse graph, you've got to plot the points of the exponential graph first, because we know how to plot that. Okay, so you've plotted your coordinate pairs. Here are all my coordinate pairs. I've plotted my asymptote. Very important. Can't touch this. Please remember, always remember to plot that asymptote, because it shows you where your graph tends towards. Infinitely tends towards the asymptote, but doesn't touch it. So here we go. We've got the inverse of x, which is y is equal to 4 to the power of x. Now we need to swap these guys around. So, and I've got it as coordinate pairs because it's vertical. Remember, x cannot be 0 because we swap our x's and y's. And that's how we draw our log graph. We swap our x's and y's. So I'm going to have a few values here, and I'm going to quickly draw it out for you. Okay, so I've plotted this one. It's y is equal to log base 4 of x. Please write down all of your coordinate pairs. You get marks for the writing down coordinate pairs. You get marks for your asymptotes. Please label your asymptotes as x is equal to 0 or not equal to 0, however you want to label them. And you can see how this vertical column really works, because you can immediately get your coordinate pairs and you don't have to do much more work than that, and you don't have to write out lots of little sums on the side to try and find out what y is, if x is 0 or if x is 1 or if y is half or something. It's very neat and it's not time consuming. So if you've got any questions, please let me know. Another thing to know is, very importantly, how to solve for an equation that has a log in it, but you should do that at school. And if I've got something like this, if they say solve the log, and it's got for instance, log, you know that log base 2 of x is 3. You know that that thing is going to be 2 to the 3 equals x, so 8 equals x. So if I've got a log of base x to the 8 equals 3, I've got a base and a growth of a growth rate. A rate of growth is 8, and I can see that thing, I can either cube it. What am I doing minus? It is 1 in the morning. I can either cube both sides, or I can see that thing is going to be 2. Okay, so cube both sides. So learn some of your log laws, and remember to draw the sketch of the exponential first, and then the graph of the log.